Okay, so hello and welcome to my talk on declarative programming. This is a talk about making the computer do the trivial, repetitive, and error-prone stuff, which I believe is a very noble cause. So I don't know about the rest of you, but for me, one of the coolest aspects of programming is that it lets me be lazy. I've always been really compelled by this idea of automation and making the computer do the hard work, and I really like trying to harness the computational abilities of the computer. So last semester, Nico gave a talk that ended with a slide that has this quote from Sam on it that I found to be very powerful. It goes like this: "Life is like Vim. There are a lot of shortcuts, and you should take them." I found this quote to be very compelling because I think it is very true. Some things in life are kind of supposed to be hard, and they are useful because they are hard, like going to the gym or doing leak code. But most other things, if you really find yourself banging your head against the wall and really struggling to get something done, chances are there is some easier way to do it. And I think it's a very valuable skill to try to be able to recognize these situations and to find the shortcuts and to take them. So that's kind of what this talk is about. It's talk about applying that idea to programming, because I think programming is no exception to this rule. Usually when we think of programming, we think of imperative programming, which is kind of like outlining a series of instructions for a computer to follow out in order to accomplish some goal. But declarative programming, on the other hand, is like, instead of trying to tell the computer how to do something, we just want to tell it what to do, and the computer should do the work in figuring out how to do it. So in this way, declarative style is kind of like the Vim, but for programming. So like Vim is all about kind of harnessing the computer to make text editing as optimal, as efficient, as natural as possible for the human. Declarative style is like the same thing, but for programming, right? So we want to make programming natural, safe, and optimal for the human by harnessing the power of the computer. And the way we do this in Vim is by trying to minimize the usage of the mouse. And the way we do this in declarative style is by trying to minimize the usage of explicit control flow. So you might then be asking, like, what? Minimize control flow? Like, isn't that control flow the essence of programming? And when we think of things in a declarative light, that's kind of, it does seem to be the case. Like, I mean, indeed, that is actually what's happening in assembly, right? It is executing instructions, but this actually isn't the way we have to think about things. And in fact, there are some languages that we use all the time that have minimal to no control flow whatsoever. So maybe we can look at these languages and try to apply these ideas into more general purpose programming to get the same gains. So one such language is SQL. Here is some SQL code that ranks students based on the number of LeetCodes they have solved. And we see we've got the select here. We've got like some columns we're selecting. We're saying from this table we want to do this join between two tables, and we're doing like this where clause, which is like a filter, and there's this order, which is like the sort. So we're like really describing to the computer what we want, but we're not telling it exactly how to do it. We're just telling it what we want, and then there's the compiler does this thing through a process called query planning that converts this higher level relational logic into low level like for loops and like operations on B trees and hash tables. So we really kind of like this idea that we can describe things at a high level. And key thing to note is that there is absolutely no control flow in this code. Another example of this is Svelte. Gil gave a talk on Svelte a while back. Check out the video. But Svelte is a web framework, if you will. It's a tool you can use to write dynamic web pages. Here's some Svelte code that dynamically converts Fahrenheit to Celsius. You see we've got this Fahrenheit variable up here, and then we've got an input tag down here that binds the value of Fahrenheit. So basically, whenever the user updates this input tag, the Fahrenheit variable will also be updated. And then we got the Celsius variable here, and there's this $: thing, which basically means to dynamically update the Celsius variable. So basically, whenever Fahrenheit gets updated by the user, Celsius will then be recomputed, and then it will also be rendered down here in this paragraph tag. So here we have this like dynamically updating web page. Yet we're not specifying any control flow here. We're just kind of specifying like relationships between things on the page, and the computer does the work of abstracting all these dirty like DOM manipulations and event stuff like that. So I think we can agree that both these examples are really kind of like a nice way to write code. We really like writing code that is like this, that's very high level. And by getting rid of control flow, we're able to make these new kind of higher level abstractions, getting rid of query planning and dealing with the DOM and stuff like that. And by doing so, we're able to kind of shave off a lot of these low level jagged edges that we used to have to deal with. To write code that's a lot more safe and a lot more kind of high level and has a lot more guarantees when we compile. So these two languages, we kind of use them all the time, but they're really just the tip of the iceberg when it comes to declarative programming. There are many more tools out there to do things like this with minimal control flow. And I'm going to go through a few of them real quick here. So QAP is a Rust library. It stands for command line argparse. It lets you write command line programs that parse arguments. And one really cool feature of QAP that I like is that it lets you write one of these programs simply just by defining a data structure. So here's an example. We've got this struct here called CLI settings, and it's got this field called image file, which is an option of a string. And all I have to do is I just write derive clat parser up here, and then this will generate this parse method for me that I can then call down here in the main method, and then I get this command line program for free, basically. So key thing to note, no control flow in this code. I just specify higher level relationships, and I get the code for free. APL is another example. APL is an array programming language, which basically means that we write in these funny squiggly symbols that we call glyphs. And each one of these glyphs is an operation or a transformation on a multidimensional array or a tensor. And the way we kind of traditionally code an APL is by stringing together a bunch of these operations. And as a result, we can kind of forgo explicit control flow because we're using these transformations instead of that control flow. So this results in code that's kind of much more of a declarative style. And we can kind of describe things in terms of relationships instead of low-level incremental changes. Prolog stands for programming logic. It is a logic programming language, which basically means instead of writing functions, we write a database of predicates, and then we can then use the Prolog program to execute queries on this database, and we can leave some of the arguments of the predicates variable, and Prolog will give us all of the possible values for those variables. So it's kind of a lot to parse at once, but in a nutshell, this basically means that we can run functions backwards. So one example of this is that if you write a Sudoku checker in Prolog, you get the solver for free, because Prolog will basically do the backtracking for you kind of behind the scenes. And this is done by abstracting away the unification algorithm, which is what the same algorithm that's used in type inference in programming languages. And we can kind of apply this to a lot of cool things. You can write parsers very nicely in Prolog. And in fact, it's most commonly used in computational linguistics. But there's a lot, really anywhere we're using these kind of higher order logic things where we're relating things with predicates, we can apply this, and it's a very declarative style. There is no control flow in this code. So all these examples that we've seen we would probably consider DSLs, domain-specific languages, which basically means we're kind of working with these very specialized things as opposed to something that's more general purpose that we can use kind of every day. All of these are kind of writing code for a very fine-tuned use case, right? And in this way, DSLs are kind of like Vim macros, right? Because they offer a really high amount of power because we're able to write very little code and get a lot for free from that, but at the expense of high specialization, meaning that we can only use these things for that one very finely tuned use case. So then this kind of naturally leads into the question, what about the core Vim bindings? Like our bread and butter of Vim are the core Vim bindings that we use every day. We don't use macros to do things, but we use something that's maybe a little less powerful than macros, but is more general and we can apply everywhere and we can use all day, every day, right? So what is the equivalent of this for declarative programming? And we can kind of go back to this question about minimizing control flow. How can we apply this to general purpose programming? And at first, it might not seem trivial how we do this because, again, we're kind of taught to think about things in an imperative way. So it might almost seem like it's impossible. Like certainly, we cannot have a general purpose language that has no control flow whatsoever, right? Well, enter Haskell. Haskell is a general purpose language without explicit control flow. So how does it do this? Well, in Haskell, we write code by writing a bunch of functions and then combining them together, right? And it's kind of not unlike other languages, and then we can kind of break down the anatomy of a Haskell function. We got a lot of the same things that we're used to, like function name, type signature, arguments. The key difference here is that the body is just one return value. There's just one expression in the body, and it's just a return value. We do have this notion of local variables, but these variables are immutable, meaning they don't change over time. Also, so there's no notion of control flow, and they also cannot cause side effects. So you can't have one of these variables going off and doing something else, right? Really, they're just kind of like a syntax sugar for aggregating values. The only way we use them is to harvest their values to then use them later in the return value. So we can kind of juxtapose this to what we usually think in C or in other imperative languages, where the body of a function is kind of this list of statements, which can contain whatever control flow you want. It can have looping, can have modification of variables, mutation, whatever you want, and this is a much more imperative way to look at things, right? While in Haskell, it's very declarative because we're thinking of things relationally, and we have to kind of use more higher order constructs to get the usual programming things we want. Here, we use kind of low-level stuff to emulate that same thing. Another way expressions are a lot more declarative than statements is that statements are not type-checked. They're kind of type-checked by the programmer, while expressions are type-checked by the compiler. So again, kind of the computer doing the work, because statements really the only thing the compiler knows about them is that they are things that are separated by semicolons and they can cause effects, right? So we can often rearrange them or remove them or add them, and the compiler will be okay with that unless there's like some sort of like variable naming error or something. But most of the time, the compiler just says okay, and then it just ends up as a runtime bug. But when you have expressions, right, the compiler, if you rearrange them or add them or remove them, chances are the compiler will catch that. So this results in code that is much more robust and safe when you compile it. So the typical way we try to code in a more declarative way in general purpose programming is we take these things that we traditionally wrote as statements that use kind of traditional control flow, and then we convert them into expressions that use less control flow and have more guarantees by the compiler. So one example of this is iteration, right? So like for loops is kind of your traditional statement that we use. And the other hand, the equivalent expression is stream processing, which is like your map, filter, and reduce. So even just like kind of looking at this code just kind of glazing over it, you can see that the declarative version is obviously much more kind of just telling the computer what we want instead of how to do it. If you even just look at the function name, min non-zero length, and then you look at the function body, min filter non-zero map length, right? We're almost just like telling it what to do instead of telling it how we want to do it. And then you can kind of juxtapose this to C or whatever other imperative language of your choice, right? And we're like initializing all these variables, things are changing over time. It's just like it's kind of a huge mess, and it's very easy to imagine there's all sorts of bugs in this code, and there probably is for all I know. I didn't check it, but there's so many more guarantees in the right, and if this declarative code, if it compiles, chances are that it works. This is actually a pretty well-adopted idea in other languages. You've probably heard map, filter, reduce, right? And you can do this in most of your favorite language. You can start doing this today if you aren't already, right? Here is the equivalent code in Java. It might be a little bit more verbose, as Java usually is, but it is the spiritual equivalent in Haskell, and you can even notice that here is a function in Java with a body, but there is only one expression as a return expression. So it kind of mirrors what Haskell does, but in Java. So you can apply this to your day-to-day programming. So selection is another example of this where we have statements and it can be better expressed as an expression. Basically the idea is we have the switch statement and we want to have this conceptual return value from the switch statement. And in order to do this, because a statement is a statement and it doesn't return a value, we have to have this external res variable. And then in each of these case arms, we have like an assignment to that res variable, right? And then we can finally use it down here. With the expression equivalent, we can just have one single let res equals, and then we can have the whole case expression all together, right? And the compiler guarantees not only that all of these arms return a value, but also that all of these values are of the correct type. And then we can finally call the show res at the end. But we can even go one step further and eliminate this res variable entirely because the case expression is indeed an expression. So we can just get rid of it and call show on that case expression straight off the bat. So this is kind of applies to even things beyond switch statements like if and else and stuff like that. Often we have to use these extra variables in order to get the same thing as that we conceptually think of as an expression, but we have to use kind of these dirty hacks to get that in a statement, so it's more naturally expressed as an expression. So you might be then saying like, okay, like maybe this Haskell code is a little bit better, but like it's not that much better, right? Like I'm so used to coding these things in the imperative way. Why should I go through the effort of writing it in the declarative way if it's really not that much different, right? And I would argue that maybe, yes, you're kind of right at a small scale, but once you start adding more and more things to your program and things get more and more complex and you're trying to keep track of things in your head, when you're using these much more brittle, low-level structures, when they scale up, you end up with like a tower of toothpicks, right? And there's so many ways a thing can break. But when you instead use declarative programming and you get the computer to do the work of these low-level checks, you're building a tower out of Lego bricks where you have these really robust low-level structures that scale up in a very nice way and things don't break. So that's kind of how we kind of get this phenomena in Haskell where when people who are used to traditionally imperative coding in an imperative way, and then they start switching over to Haskell and start using this more declarative stuff, they're often amazed to see that once they get their program to compile, it just works. Like they just run it and it works, right? And that's because they feel like they're almost getting away with something because they're so conditioned by when they program in imperative languages, they're so used to having all these bugs that pop up because the way we program imperative makes the human do the work instead of the computer. And when the computer does the work, we can kind of even eliminate all sorts of usual types of errors that we run into just kind of by construction by using these more robust low-level structures in declarative, right? So when we're not using explicit indexing, we're not going to have any array-bound errors. If we don't use pointers, we can't have null pointer errors. Off by one errors are pretty much gone when we use stream processing instead of explicit for looping. And runtime errors, even in general, can be mostly, if not completely eliminated when you use less and less partial functions. So this all sounds pretty great, right? So why doesn't everybody use Haskell? And you kind of got me there. But the answer to this, why is this? It's actually pretty simple. It's because in the same way where with Vim, usually the keyboard is better, and we usually like to use the keyboard, sometimes it just makes more sense to use the mouse. And in the same way with declarative programming, most of the time it is better, it is a better abstraction, but it doesn't always work because that is indeed, computers actually do work in an imperative way, and some things are better expressed as imperative code, and the world isn't made out of Lego bricks, you know? So like, here's an example of some code that is really naturally imperative, kind of inherently imperative, and we try to port this over to Haskell, we get something that's very complex. And this becomes more and more complex, it becomes more and more complex in Haskell, and it kind of blows up, because Haskell is inherently designed to be something that makes programming in declarative style much more natural at the expense of making imperative less natural. So what I hope the big takeaway here is that while Haskell might not be our end-all be-all tool to fix all of our problems, it is certainly a valuable learning tool in order to better acquaint ourselves with this declarative style and building things that have the computer do more work and are more robust at a low level and scale up better. And I think that even if you don't learn Haskell, declarative style is something you can apply in your everyday programming and something that you can use and really see the gains from. Personally, I've seen a lot of improvements in my own code by adopting this style, and I hope that you can as well. That's the end.